WASP-39b is 700 light-years away, and Webb never photographs its atmosphere. Still, the telescope has measured carbon dioxide in it. How can filtered starlight during a transit identify gases on a planet Webb cannot resolve? WASP-39b is not an Earth twin. It is an inflated hot gas giant in Virgo, roughly 700 light-years from Earth. It orbits very close to its star, completing one circuit in just over 4 Earth days. That tight orbit gives astronomers repeated transits. Each time the planet crosses the face of its star, the star dims by a small, measurable amount. The planet itself remains unresolved. Webb sees the combined light of star and planet system, not a separate little world beside the star. During most of the transit, the planet blocks starlight with its opaque body. At the edge, the geometry changes. A tiny fraction of the star's light skims through the thin ring of gas around the planet, before continuing toward Webb. That ring is the limb of the atmosphere. It is not photographed edge-on. It is sampled because some starlight has passed through it. The useful signal is the difference between light from the star alone and light from the star while the planet and its atmosphere are in front. NIRSpec separates the arriving infrared light by wavelength. Transmission spectroscopy then asks how deep the transit is at each wavelength. Molecules are not gray filters. Carbon dioxide, water vapor, sodium, potassium, and other gases absorb light in particular bands set by their molecular structure. Where a molecule absorbs, less starlight gets through the limb. At those wavelengths, the planet appears slightly larger because its atmosphere has become more opaque. The problem is now narrower. A change of a few hundred parts per million has to be turned into a chemical identification. For WASP-39b, the established carbon dioxide signal sits near 4.3 microns. In NASA's public spectrum, it appears as a broad rise in transit depth, a hill stretching roughly from 4.1 to 4.6 microns. That shape is not a rainbow photograph from the planet. It is a wavelength-by-wavelength measurement of how much starlight was missing during transit. Webb's NIRSpec observations detected carbon dioxide strongly, and later analysis of the 3 to 5 micron spectrum reported an average uncertainty of about 221 parts per million per spectroscopic bin, with carbon dioxide detected at 28.5 sigma. The error bars are part of the result, not decoration. They show how much the measured transit depth could shift because of photon noise, instrument behavior, data reduction, and other systematics. A strong carbon dioxide feature can survive those limits while other details remain model-dependent. Temperature structure, cloud properties, chemical abundances, and circulation are not read directly from the spectrum. They are inferred by comparing the data with atmospheric models. Different assumptions can fit some parts of the spectrum almost equally well, especially when aerosols, temperature pressure profiles, and chemistry are allowed to vary. That is the answer to the contradiction. Webb does not need to photograph WASP-39b's atmosphere to identify some of its gases. It needs a transit, a stable star, and a spectrum precise enough to show that the planet blocks different wavelengths by different amounts. For WASP-39b, the evidence supports a strong carbon dioxide detection, along with other molecular and atomic features reported across Webb's instruments. It does not support a complete weather map, a direct image of clouds, or any claim about life. Exoplanets are becoming measurable environments, but for now, many of those environments are still known through shadows, filtered starlight, and carefully bounded inference. That's why source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.